Good morning, everyone. My name is Abhijit again. Let's make the inverter layout today. I've already created the library and the and the layout file. Let's go to preferences. There's a couple of things I need to show you. So the scale remains the same, just for the symmetry and continuity. And go to tools, check the spice simulator. Done. Go to display grid. Check the size 4, which is 1:1 horizontal to vertical, and click OK. So we have set the initial setup. Let me show you the actual diagram of a stick diagram for inverter. This is how it looks. So this is the VDD and this is the ground. PMOS, NMOS, and the drain connections, source connections, input and output. So it's pretty simple. Let's start with the PMOS. So since we are going to simulate this one, click on it. We need to set a spice model, the same spice model that we had set during our inverter schematic. Now the spice model, that text is beneath the PMOS over here. So take control. Yeah. So now this is selected. Control I, PMOS, enter. Done. So we need to size the PMOS. PMOS I'm taking as 10. Rotate by 90 just so the connections are simple. Done. Now any connections to the PMOS. So these are drain and source, or source and drain or source, anything, because drain and source are almost similar in the present technology. So to make connections we need an active region. So this is the PMOS drain and source regions, and if we need to make a chip out of this, I need to take connections out into the pins. So for that I need active regions, one for the source and one for the drain. So there's P active, take 2. Now size it equal to the PMOS itself, rotate it 90. Done. Similarly this one. So now you need to make connections. So click on any side of the PMOS and you'll see a bar coming over here. This is the place where you connect the PMOS to the active regions. Right click on the bar, hold it and drag towards until it gets locked on. As you can see, at this point of time it gets locked on. Leave it all. So the connection is done. So there are two wires that are over here. So any point of time you need to select two components and edit common properties. Click on one, hold shift, click on the other. So there are two wires that are connected. Double click, and at any point of time in the design you might have to move the components around. So it will be a big hassle if you have to move the wires also. Instead of that, go to extension, make neither and extend, apply. Okay, so now I can easily move this active region closer. So as you move, there's a spacing data that comes over the active region. As you can see, P active spacing is 9.5, 10.5, 11, 12.5, 13.5. The minimum is 3.5. So to save space, I will go until 3.5. If you go further, there's an error. So yeah, similarly this. So the PMOS is done along with the spice model. Let's quickly do the NMOS also. So yeah, now we're done with both PMOS and NMOS and the connecting active regions that are there. So these two are the different substrate areas. We can move them closer to just to save the area because silicon is pretty costly these days. So yeah, but you shouldn't overlap them. Just go one step down. So yeah, this is the closer that you can get. but if you can achieve a proper overlap, always go for it. But that's not the aim of this tutorial. And so yeah, we've done the PMOS and the NMOS. Now let's make connections. I'm assuming this is the drain. I could easily assume this is the drain of the both. So click on one, right click, extend down to the other, lock down, done. Now there's a single input, so which means that the gate should also be shorted. Select one gate, right click, extend onwards, lock down, done. So we made the connections. Now we need to give the input and output ports. The problem with polysilicon is that you cannot take it outside the chip. So if you were to make a connection outside the chip, you need to make a metal connection. But for that, there you need a metal to polysilicon contact, which is this, and then you need a metal contact which you can later take outside. So let's connect this one first. So there is a metal area coming in. Instead of that, you can always extend the polysilicon area, because metal, as much as metal is there, and then there is, so a lot of metal basically lead to a lot of power consumption. While that is not a big concern in that design, let's just make it a standard. So select the gate, right click. As you can see, there is a polysilicon that is extended. Now move it inside this one. Done. So now we need to make the connection from the metal. So this, as you can see, is a huge thing coming out. Instead of that, go from the metal, which is a smaller one. Done. And this is the input port. So Control E, we make an export. We done. Move it inside just to make the design more compact. There have the input port. Now the output port's advantage is there is an already metal connection, so you don't have to make the metal to poly contact. Just go for the metal contact, make a connection from the reverse. Now give the export name. This is the output port. V out and move it inside just for better compactness. So we're done with the connections, and the other connections that are left are VDD and ground. There are two ways to do this. Take a metal line and make a connection over here for VDD and then for ground, and connect corresponding substrates. So as we know, PMOS substrate is connected to the VDD, and that of NMOS is connected to the ground. So instead of that, what I prefer doing is take an N well for PMOS, put it on top. Similarly, P well for NMOS, put it on the bottom. Now extend it until all the mosses are until all the mosses are covered. So the bigger moss over here is PMOS. So, and it has a size of 10. So give 20, double of that, so that it gets covered. And anything we need to change? No. So we have it over here, and then same for the VDD. Now make the source connections. Control S F5, no errors found. So every time you do something new, make a you make a connection, you draw a wire, something of that sort. It's better to save it once and go for F5. That will make the initial design checks. So now let's go for the source connection. Done. Done. So all the connections are done, but for the simulation to run, we need all the ports named. So this port, as you can see, if you hover over it, there's a small blue bar that comes over here. Select that, Control E, input port. This name is VT. Done. Similarly for the ground. So ground, VDD, V in, V out, everything is done. Now we need a spice code. So I already have a spice code that I've written during the schematic. I'll just copy the same thing, miscellaneous, spice code, and I just change the input port names. So it's not case sensitive, the case doesn't matter. I'm just being sure that I'm not making any kind of errors. Control S, final F5, and there's another electrical rules check that you can do. ERC tools, ERC check wells. Done. You don't need the antenna check for this one. So yeah, we're done with the design. Now let's simulate it. So LT Spice has opened up. we've done all the design rules and all the checks. So LT Spice just receives the spice code from electric through the layout. Select V in and V out. Okay. Now this. As you can see, the traces are added. Now just to show this is an inverter. There you go. The inverted action is done. So that brings us to the end of this tutorial. Thank you.